Hello and welcome to my video, lesson 2.3 on electric fields. So electric fields are also similar to gravitational fields. In the last video we looked at electric forces compared to gravitational forces. Now we're looking at electric fields compared to gravitational fields. They're the same sort of thing. The only thing is that we can have lines towards or away because there could be a repulsion or a attraction. Now, with only one object, it's kind of hard to tell if it's repelled or attracted. So what we do is we pretend that there's a small positive charge in the field, and what direction would it be pushed or pulled? That's the direction of your field lines. So let's put a positive charge here in a negative field. Well, if it's a positive charge, it's attracted to the negative charge that's causing the field. So therefore all the lines are going towards. But if we put a positive charge over here, well, it's being repelled from the initial source that is positive, so that's why all the arrows point away from the center. So that's kind of the directionality to it. Let's take a look at some example questions. So here are a couple example questions. If you can, try it yourself right now, and you can pause the video. Whoops. You can pause the video, try it yourself, and see how you do. Okay, if not, that's okay. Here's the question. Charge A is on the left. Okay, it's going to be negative 4.5 microcoulombs. And then there is a 4.5 centimeter gap, and then charge C. Actually, I'm gonna do a bigger gap than that in terms of my drawing here. And then there's gonna be C over here. Okay, which is positive 2 microcoulombs. Okay, so it's asking what is the net electric field in the middle between the two charges. So the middle is going to be here. So if we just go ahead and figure out what the distance is from here to here, and from here to here, we can work with this. So it's going to be half of the original distance. So it's going to be 2.25 centimeters, 2.25 centimeters, right? And that's the position, I'm going to call it point P, that we're looking for the electric field. Okay, not force, electric field. It's kind of the same sort of thing, but not quite, because there is no actual particle there. Okay, there's no actual charge being affected by it, so there's no force. But we're imagining what would happen if we did put a force there, and by finding the field, you can find the force in reverse. Okay, so if we imagined a little positive particle, what direction would the positive C be doing to it? Well, it would push it in this direction. And the negative A would pull it this way. So it would attract, right? And it would repel over here. Okay, with that in mind, we can now see that the two different arrows are going to add tip to tail, right? So we're just going to take the electric field, which we normally go like this, the electric field for A, okay, and we're going to find that, and we're going to add it to the electric field for C. Okay, so this one's going to be KQA over R squared. This is going to be KQC over R squared. So electric field net technically it needs those lines, but normally we kind of get a little bit lazy with that. Okay, it'll look like this, and now we can plug it into our calculator. So 8.99 times 10 to the exponent 9 times by A, which is 4.5 times 10 to the exponent -6, because it's microcoulombs, over r squared, which is 0.0225 squared, plus k, which is, let's do it this way, 8.99 times 10 to the exponent 9, over, times by c, the charge on c, so 2 times 10 to the exponent -6, because it's microcoulombs, 0.0225 meters, and we get an answer of, wow, that's a wild answer. I don't know if that's kind of normal-ish, but there's our answer. Times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Times 10 to the 8. This is newtons per coulomb. That is our final answer, although we should say that it's pointing to the left. And that's our final answer. Oh, and sig digs. 2 sig digs to start, because 4.5 is 2 sig digs. So 1.5 is our final answer. All right, let's take a look at example 2 now. Similar sort of idea. Pause the video now and try it for yourself. All right, so the big idea here is that this is going to be a 2D vector question. So we're going to just start with point P. Okay, I'm just going to pretend that that's point P, and we're going to have a charge to the west. And I'm going to call that charge A, which is positive 2.4 microcoulombs, and it's 3.7 centimeters to the west. Now, if we look at charge C, it's to the north, and it's over here, so it's positive 1.2 microcoulombs, 6.2 centimeters to the north. Okay, so there's what it starts with. Now, what we have to remember is if this is an electric field, we always pretend like it's a positive point. Okay, if it's a positive point, these are repelling. Both of them are repelling. Okay, now they're not always both doing the same thing. This example, they're both positive, so they're both repelling. So they're both pushing this way. So from point P, okay, we have a force this way. Not a force, an electric field this way, and we have an electric field this way. So this is, I'm going to call it A, the electric field from A, and I'm going to call this EC, the electric field from C. Okay, so the net field is going to be this. If you add the two vectors together, tip to tail, it's going to look like this. And we'll look for the angle there, and we're going to look for the net field. Okay, so now we're going to use two different methods to solve this. We're going to use Pythagoras, so c squared equals a squared plus b squared. So we're going to use E net square root of EC squared plus EA squared. And to find the angle, it'll be theta equals tan -1 of opposite, which is EA, over adjacent, which is EC. Okay, so we're going to find the angle, and we're going to find the electric field net. Okay, what I recommend that you do here is you just recognize that the you're using the same number twice, so you may as well calculate it first. Normally I say do the algebra, but in this case I think it might be easier if you just calculate it first. Okay, so let's find EC and let's find EA. Now to find those, we're going to use the same formula as we did on the last question. So the electric field is KQ over R squared. So that's the formula we're using. So it's going to be 8.99 times 10 to the exponent 9 times, let's do C first, so 1.2 times 10 to the exponent negative 6 over the distance 0.062 squared. So this is going to be 2.806 times 10 to the exponent 1, 2, 3, 4, 5, 6. And this is newtons per coulomb. Okay, and then we're going to do the same thing for A. So it's basically the same expression, but we're changing the distance to be 3.7, so 0.3037, and we're changing the charge to be 2.4. Okay, so other than those changes, it's the same sort of thing. So 1.576 times 10 to the exponent 1, 2, 3, 4, 5, 6, 7 newtons per coulomb. Okay, so now we have both of those A and C electric field components, and now we're going to plug them into the orange formulas and solve for our answer. So let's do the first one, the Pythagoras version, to find the E net. So we're going to take the first one, square it, plus, this is going to be a big number, this is going to be a very big number. So we get 1.6008, I think, times 10 to the, I'm going to guess 8, but let's see. 1, 2, 3, 4, 5, 6, 7. Nope, times 10 to the 7. Newtons per coulomb. Okay, now let's deal with the angle. So it's going to be tan negative 1 of, now let's make sure we do the right one. So this is going to be opposite over adjacent, so it's A, so it's going to be this one over the other one, so 28,06451.613, and we get an angle of 79.9 degrees. Okay, so our final answer will be 2 sig dig, so 1.6 times 10 to the 7 newtons per coulomb. 2 sig dig, so 80 degrees, east of south is our final answer. Alright, so I hope this video helps you better understand electric fields, how to solve things, and also understanding that it's from the perspective of a positive charge within the field. That's how you decide the directionality. Hope this video helps, and good luck.